Hi everyone, in this video we're going to start topic 8, and in topic 8 we're learning about one thing, which is how to draw Lewis dot structures, and we're going to spend a whole topic talking about it because it's relatively complex and I want you all to get good at it. So this is essentially what we're going to be learning to make. This structure right here, this is what we call Lewis dot structure. So we had talked last chapter about determining whether a chemical is polar or nonpolar, right? So we had talked about ammonia and ammonia NH3. If you're just given NH3 and asked to say, is it polar or not? Well, it's kind of hard to know because we don't know if NH3 looks like this, if it's trigonal planar like this, or if it's trigonal pyramidal like this. And the only way to know is to draw the Lewis structure. So we have to be able to draw it. So we've got to become a great sketch artist in order to figure out these puzzles. Okay, so we're going to dive into how to do this. So let's say you have a molecule. We're going to use CO2 as our example here. We're going to start with this one. So the first step when you draw Lewis structures is that you want to choose your central atom. So the central atom is not always going to be the one that is in the center of the molecular formula. So you might see something like this. It's not always that the one in the center is the one that's the central, or the one before that's the central, the one that's after. The way we determine this is to use the least electronegative atom. Least electronegative atom will be your center atom. So in this case, if you go to the periodic table and you look, you see that we've got carbon, nitrogen, oxygen, fluorine. And so because oxygen is closer to fluorine, it's got more protons, it has more pull on its electrons, then it's going to be more electronegative. So our central atom here is going to be carbon. So this one is going to go in the center of our structure. Hydrogen is an exception. We're going to talk about this in a little bit, but do know that hydrogen is never the center of a molecule. It can only have one bond on it, so you may want to go ahead and write that down. Hydrogen can only form one bond. One bond. So therefore, it is never the center of an atom. So do not make that mistake. Okay, so our first step in drawing Lewis structures is to bond all of our atoms together in a skeletal structure. We will change this over time. So we're just going to go ahead and give it our best guess to start with, and then we'll modify it as we go on. The same as like how we balanced equations. We gave it our best guess, and then we kind of modified it as we worked. So the first thing we're going to do is we're going to take our central atom, which is carbon, and we're going to stick it in the center here, and we're going to attach the two oxygens to the sides. Okay. So you might wonder, like, why don't I put an oxygen here or an oxygen here? For our purposes right now, it doesn't really matter. We're going to learn later on why it's going to be fit in that structure. So the only way that you'd have oxygen atoms like at a right angle like this is if you had some lone pairs over here pushing them that way. So we're going to have to figure out, are there lone pairs here that are doing that? Or is there no lone pairs and is it straight? So we're going to talk about how to do all of that. Okay, so give this a try on your own. So if you have a molecule consisting of nitrogen and oxygen, which atom would be at the center of the compound? If you had a molecule consisting of bromine, oxygen, and carbon, so carbon, oxygen, and bromine, which atom would be at the center of your molecule based on what you just learned? Let's take a look at how to answer this one. So the way that we know which atom is at the center of our molecule is the least electronegative one. Least electronegative one. Okay. So for our first one, nitrogen and oxygen, this one's pretty easy to tell. Oxygen is more electronegative because it's closer to fluorine. So nitrogen is going to be at the center. So this would be your central atom. We don't know how many oxygens are here yet or how many nitrogens. This problem doesn't really tell us. All it's asking us is to choose the least electronegative atom, and we're going to put that at the center, okay? So let's take a look at carbon, oxygen, and bromine. I'm actually going to look this one up because it might be a close call. So if you're ever in a situation where it's hard for you to tell which one is more electronegative, like all the atoms aren't in the same row or the same column, you can always pull up your Pauling scale to check. So on this Pauling scale, you can see here that carbon is 2.55, bromine's 2.96, oxygen is definitely the most electronegative. So carbon here is the least electronegative out of these three. It's at 2.55, where bromine's at 2.96. So carbon is going to be our central atom. So that means that carbon is our answer for this one. So feel free to use the Pauling scale if you ever get stuck and you're not certain about electronegativities of things. Let's look at the second step of drawing Lewis structures. The next thing we want to do after we get our skeletal structure together, we've chosen our center atom, is to place electrons around the atoms. So how we do this is we need to find out how many electrons we're supposed to place in the first place. Sorry, I kept saying place, so I tried to cut it out the second time. Okay. So we're going to figure out how many electrons need to be on the structure in general. And how we do that is we go to our periodic table. And what we want to do is we want to count the total number of valence electrons that each atom contributes to the molecule. So we're going to go here to our oxygen and here to our carbon. And we're going to find out how many valence electrons it has. So you might be wondering how this ties into topic 1. This is how it ties into topic 1. We need to know how many valence electrons are in each of these atoms so that we can calculate their Lewis structures. So oxygen is in group 16, or 6A, so it's going to contribute 6 valence electrons. Carbon is in group 14, or 4A, so it's going to contribute 4 per atom. So carbon's going to give us 4, oxygen is going to give us 6, and this oxygen is going to give us 6. So we want to find the total. So we're going to add all these together. So inside of this carbon dioxide molecule, we need to place 12 and 4 is 16 total electrons. So around this carbon and around these oxygens, we have to put 16 electrons on them. Now, sometimes you may see charged molecules. So you might see like CO2 minus. This minus here is an electron. So in the scenario where if you had CO2 minus, you'd have 16 electrons plus 1 more extra electron that comes from this charge. If you see a plus charge, we do the opposite. So if it was CO2 positive, this is loss of an electron. Okay, so we do 16 electrons minus 1 electron to give us a total of 15 electrons. So this one would be 17 total. So you can see how the total number of electrons changes if there's a charge on the molecule. Okay. Remember that we've already placed 4 electrons on the structure because inside of a chemical bond are 2 electrons. So we've already got 4 electrons in our structure. We're going to have to place the remaining 12. Okay. And we're going to cover how to do that in step 3. All right, so now you try. How many total electrons would be placed on the Lewis structures for the following molecular compounds? This is the compound made of nitrogen and oxygen that we talked about the first time, and then the compound made of carbon, bromine, and oxygen that we talked about as well in the first question. So make sure you use your group numbers, and you watch out for your charges. Let's take a look at how to answer this one. So nitrogen is in group 15, or 5A, so it's going to contribute 5. Oxygen is 6, it's going to contribute 6, and we have 3 of those oxygens, so 6 plus 6 plus 6, and we have a minus charge here, so we're going to add 1 more electron. So this is how many total electrons will be in this nitrate structure, NO3 minus. 18 plus 6. So that should be 24 total electrons. Cbr2 oxygen, so carbon is 4, it's right here, it's 4. Bromine is right here, it's 7. So plus 7, we've got 2 bromines, so I'm going to add 2 of those. And then our oxygen is right here, it's a 6. Add all of those up, and you get 24 electrons again. Okay. One way to check whether or not you might possibly be correct is to make sure that this is an even number here. It doesn't always mean you're going to be correct, but it's definitely wrong if you have an odd number, because odd numbers are radicals. Remember, electrons come in pairs. So if you don't have an even number, that means you've got an unpaired electron floating around somewhere. It doesn't mean it doesn't happen. It can happen, but the majority of the time, you should have even numbers. So if you calculate an odd number, double check your work. Something could have gone wrong. So this can occur. It can occur to have an unpaired electron, but it's not often. Okay, so do be on the watch for that. All right, let's move on to step 3. So for step 3, after we've found our total amount of electrons, we've drawn our skeletal structure, we're going to count the remaining electrons that are not already in the structure outline, and we're going to place them. Okay, so we had 16 electrons that we said were in the structure total, and we've got 1, 2, 3, 4 already placed. So we've got 12 electrons left to put in here. And we're going to place them as lone pairs about the atoms. Now, when you place them around the atoms, we want to start on the outside, and we're going to work our way in. This is going to prevent errors. So this is a very important step. So make sure you write this down. You understand that we're going to take this step first. So we're going to place as many lone pairs on the exterior atoms as we can until we get an octet. So I'm going to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is all of my electrons. So I can't add any more electrons. What's nice is this has a full octet. This has a full octet as well. So these oxygens are pretty happy. We can see here that if we look at our shared electrons, we've got 8 electrons here and 8 electrons here, so it's happy. Now the next step, after you add electrons to your exterior atoms, is you want to put them on the central atom, if there's any left. But we've used all of them, so there are no more electrons left to put on our center atom. Now say there were 14 electrons left over. We'd put those remaining 2 electrons on our center, but there aren't, so we aren't going to do that. This is what the appropriate structure should look like. Okay. Dun, dun, dun. Now it's your turn to try this on these atoms here. So see if you can take these structures that you've created the skeletal structure for and place lone pairs around each of the exterior atoms first, and then work your way to the center. So you'll want to use the information from the previous problems that you completed in order to complete this one. Let's take a look at how to answer this one. So it says how many lone pairs of electrons are on the central atom of each molecule. So we have our N, it's bonded to our O, 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 and we calculated last time that there's 24 electrons in the structure. We've already placed 1, 2, 3, 4, 5, 6 electrons. So what's left here is our 18 electrons. So we've got 18 more electrons to place. So we're going to start placing them around our exterior atoms first and work our way in. So let's put lone pairs here until we have full octets. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18. That's total. We've used all these up This is as many electrons as can go in the structure. We cannot stuff any more electrons on the structure. That's it. So the answer to this question is 0. There are no lone pairs of electrons on the central atom of the molecule. We have electrons and bonds around here, but a lone pair means it's not bonded. There's nothing like that there. Okay? So the answer for this one is 0 electrons. Let's take a look at number 2. For number 2, we determined the first time that carbon is our center atom. So we're going to put all of our other atoms off of this one. We had also calculated that there are 24 total electrons for this structure, and so we need to place all of those. Right now, we also have 6 electrons already placed. So it's the same thing, so -6, same thing, 18 electrons. We've got to place 18 electrons, so we're going to do that on our exterior atoms first, and then we'll work our way in if anything is left over. And I think you already know from the last example we did, there's not going to be anything left over. So this is 18 electrons. That's it. We can't put any more on there. So this one is done. Can't do any more. So there are 0 electrons right now on the center atom. Now we're going to keep modifying this, okay? So we aren't done. We aren't going to stop here. Our next step for drawing Lewis structures is to make sure that octets are satisfied everywhere. So when you don't have enough electrons to form an octet around the center atom in particular, we saw that on our last examples, we need to start sharing them. So we're going to do our carbon dioxide example. Let me see if it's here. Okay. Okay, so our carbon dioxide example, we had all of our electrons around here. Remember, these are electrons in our bonds. We can see that this one has an octet. We're good. This one has an octet. This one does not. It's only got 4 electrons that are shared between it. So we need to get 8 on it. And the way we're going to do that is by sharing these electrons by making double or triple bonds. Because we move electrons from the lone pairs into the bonds, then they're shared between the 2 atoms. So let me show you what I mean. We're going to take this lone pair right here, and we're going to take those electrons and we're going to put them straight into the bond. So we're going to make a double bond here. We're going to do the same for this one. I'll show you why in a second. Let's do this first. Okay, so oxygen, go one step at a time. We have 2 lone pairs left around our oxygen. Now we've got a double bond here and a carbon and a single bond and the oxygen. Okay, so octet is fulfilled here. Octet is fulfilled here. We still have 8. But if we look at our carbon, it's got 6. It still needs more. So we're going to keep going. We're going to take another lone pair and put it into another bond. Now, you can do this one of 2 ways. You can take one of these lone pairs and move it here for a triple bond, if you like. You can do that option. We'll learn why one option is better than the other later on. Or we can take a lone pair over here and stuff it into this bond here and make 2 double bonds. And so if we did that, that would give us C-O-O. Dun dun, dun dun, dun dun. Octets fulfilled. We've got 8 now around here because we've got 1, 2, 3, 4, 5, 6, 7, 8. Carbon's happy, and there's 8 around here, so we're good as well. So let me look at that other structure. Let me show you that other structure so you can see it. We'd have 1 lone pair remaining around this oxygen. We'd have 3 around here. If you look, our octet is fulfilled. We have 8 here, we have 8 here, we have 8 here. 2, 4, 6, 8. So either of these structures right now is technically correct, and we're going to learn in the next video why one of these is better than the other. So once you get your Lewis structure together, you need to do trial and error until you find that each atom has an octet. This is what you need to achieve, and that the molecule has the correct amount of total electrons. So remember, this cannot change. You can't increase electrons. You can't add random electrons from somewhere. You need to keep that number constant that you calculated in step 3. Okay, so now I'm going to task you with doing the same thing with the molecules that you studied. So this NO3 that we drew, you'll need to go back to your structure for that and see if there are any double or triple bonds in the following molecules. And if yes, what atoms are they shared between? Is it between, well, obviously, for this one it's going to be nitrogen and oxygen, but for your carbon and oxygen and bromine, you'll need to tell me which atom it's between, if it's between one of the bromines or the carbon and oxygen. Okay, so give this your best shot. Let's take a look at how to solve this one. So nitrogen, we had this structure made last time. It had full octets around all of the oxygens. Okay, and what we're going to do now is we're going to get an octet around our nitrogen, because our nitrogen's not happy right now. It's very sad. Okay, sad face. It's because it's only got 1, 2, 3, 4, 5, 6. It wants 8. So we're going to remedy that. And we're going to take a lone pair from any oxygen. It doesn't matter. They all are electronically actually exactly the same. So you can take it from any of them. We can just pull from this one right here. Again, it doesn't matter if you pull from any of the oxygens, it's fine. And we're going to move it into a bond here. Okay. So yes, there is a double bond in here in order to form an octet on the nitrogen. Now the nitrogen's happy. Yay. Okay. Because it's got 2, 4, 6, 8 electrons shared between it and its oxygens. So yes. And this is between the nitrogen and the oxygen. Any of them is fine. Let's take a look at the next one. So we've got carbon in the center, oxygen, bromine, and a bromine. Okay. We've got all of our electrons around our exterior atoms. Carbon right now only has 1, 2, 3, 4, 5, 6 electrons around it, so it's very sad and upset because it doesn't have an octet. It's not quite a sad face there. That's a better sad face. Okay, so we're going to take electrons from one of these atoms and move them into a chemical bond, a double bond, to share between the carbon so that it can also have these electrons. Now, as far as you all know right now, you can pull electrons from any of these atoms. And you'll learn in the next video why one type of atom is better than the other. But for now, it's okay to pull from anywhere. So you can pull from the oxygen and move it down into a double bond. Or if you like, you can pull from here and move those into a double bond. Either one is fine. So your answer for this is yes, there is a double bond. And it can be between carbon and bromine or carbon and oxygen. Either one is fine for what you have learned so far. This will not be true in later topics. Or sorry, in later videos. Oh no, I erased the whole structure. Okay, well. So it turns out like this, and carbon's happy because we've got 1, 2, 3, 4, 5, 6, 7, 8. So it's got a full octet. And all of our other atoms also have a full octet. Oxygen will have 2 lone pairs, and bromine, each of the bromines will have 3. I did want to briefly mention before you go, we are going to learn about this at the end of the topic, but I need you to know it now, which is that hydrogen is an exception to the octet rule, okay? Exception to the octet rule. Okay, right here. It does not fulfill the octet rule. It actually breaks it. So something you're going to need to remember is that hydrogen only has 1 bond total. That's all it can form. It will be hydrogen with a single bond. You will never ever see hydrogen with 2 bonds on it. This is why it can't be a center atom, because you can't put 2 bonds on it. That's because hydrogen only has 1 electron. So we can only form 1 bond with hydrogen because it's only got 1 electron to share. So it can contribute 1. And the other atom coming in, whatever it is, carbon, bromine, another hydrogen, or whatever, can share another one. But that's max how many can be shared with a hydrogen. So another good rule of thumb is to never add lone pairs to hydrogen. You just can't do it. Hydrogen is filled. Once it has 2 electrons in here, shared between it, in this chemical bond, sorry, my drawing skills, okay. You can't add any more. So we can't put lone pairs on hydrogen. All right, so what this looks like is when you draw it in molecules is you often see hydrogen kind of stuck out here like this. So you had a bromine instead. Bromine would have a bunch of electrons around it, a bunch of lone pairs. Hydrogen does not.